Welcome to the AxisVM beam modeling and design tutorial in accordance with Eurocode 2. Once you have opened the program, create a new model by clicking on the New icon. In the dialog window, replace Model File Name with Beam. Select Eurocode from the design codes and set the units and formats to EU. If necessary, you can enter the name of the project and the designer at page header. A company logo can also be uploaded. This page header will appear on the print image in documentation. Click OK to close the window. Set the view or work plane of the model. On the left side of the main window, there's the Views icon. Open it by moving the cursor over the icon and select the XZ view. The actual view is presented by the Global Coordinate System sign at the left bottom corner of the main window. Select the Elements tab to define geometry and structural properties of the beam. On the tab, the icons of available functions are displayed. Clicking on the Draw Objects Directly icon brings up the following window. Click on the horizontal beam icon. Select it even if it is already active, just to follow the step-by-step guide. This dialog window is displayed. Select Cross-Section Editor. The following cross-section editor window appears. In the window, find and select the rectangular shape icon. Enter 720 for the height and then click Place. Click anywhere in the workspace to place the cross-section, but please note, stress calculation points are automatically placed at the corners and at the center. Stress is calculated only in these predefined points. These points can, however, be modified or cleared, or more points can be added. Clicking on OK in the bottom shows a dialog panel asking for the name of the defined cross-section. Once named, click OK to close the panel, and the following message will show up. Clicking on OK brings up the following window. In the list of materials, find C25/30 and select it. Then click on OK to close the window. The setup panel will show the following. On the panel, select the Beam Polyline function and draw the center line of the beam. To define the axis line, there are several options. It can be drawn graphically in the workspace or can be directly defined by specifying coordinates. To specify the coordinates, simply type in x equals 12, enter. Then x equals 10, enter. After, right-click and from the main menu select Cancel to finish the drawing process. Press Escape twice to exit from the command of object drawing. As a result, the axis of the beam elements are displayed in blue and the contour view of the cross-section can be seen in yellow. Click the Geometry Check icon in the Geometry tab to filter the errors in geometry. In the Geometry Check panel, the maximum tolerance can be specified to merge nodes. After the geometry check, a summary of deleted items is displayed. To set the perspective view of the beam, click on the perspective icon in the Views icon on the left. In the Window menu, the Perspective Settings panel can be activated, allowing the parameters of perspective view to be modified and to rotate the model. The actual view can also be rotated while holding down the Alt key and moving the mouse. After closing the perspective panel, the view mode is preserved. Clicking on the Display Options icon allows for setting the display of the local coordinate system of the elements. The Display Options menu can be activated at any time by right-clicking and selecting the last command. On the Symbols tab in the Local Systems group, check the Beam box. On the Labels tab, check Cross-Section Name in the Properties group. Then close the window with OK. Change the view from perspective back to the XZ view mode. Then, in the Elements tab, click on Nodal Support and select the inner node. After clicking OK, in the window that appears, stiffness of the support in each direction can be set in different ways. The individual components can be defined in the global system. Reference direction can be adapted, or it can be set relative to a beam/rib or edge. Select Global Direction and set support stiffness. Rx, Ry, and Rz are the components of translational stiffness, and Rxx, Ryy, and Rzz are the components of rotational stiffness. The default stiffness value is large for high stiffness and 0 for no stiffness. Set rotational stiffnesses Rxx, Ryy, and Rzz and the Ry component to 0, and leave default values for the Rx and Rz components. Click on OK to apply the settings. Select the other two nodes and set the stiffness components of the support as earlier, but create a roller vertical support as follows. The non-zero components of the support are indicated by a brown symbol. To apply loads and support movements, select the Loads tab. Various loads and support movements should be separated into load cases. Click on Load Case and Load Group. The following window appears. The software automatically generates load case name ST1, which can be seen in the list. Click on the name of ST1 and rename it to self-weight. Then click the OK button to go back to the model space. The last edited load case named self-weight will be the active case. This can be checked on the status panel in the top left corner of the screen. Click the Display Options icon. In the Symbols tab, unselect the following: Object Contours in 3D, Cross-Section Shape in the Graphics Symbols group, and the Beam box in the Local Systems group. In the Labels tab, unselect Cross-Section Name in the Properties group. Then click OK. Click the Self-Weight icon, then select all elements with the asterisk button. After clicking OK, a blue dashed line can be seen above the beam element, which indicates the self-weight loading. Open the Load Cases and Load Groups window again and click the static icon in the Add group. Create load cases with names Live Load 1, Live Load 2, and Support Displacement as follows. Select Live Load 1, then close the window with OK. Click the Load Along Line Elements icon and select the beam on the left side. Then click OK. The following window will be displayed. The uniformly distributed load will be defined on the beam relative to the global system. Type in -17.5 into the fields PZ1 and PZ2, then confirm with OK. The negative value means that the load acts downwards. After clicking the down arrow next to the Load Cases and Load Groups icon, the following list is displayed. The list contains all the load cases defined where the current one is highlighted. Select Live Load 2. With the same method as earlier, apply -17.5 in the Z direction line load on both beams. Then change the load case to Support Displacement. Then click on the Support Displacement icon. Select the inner support and click OK. The following window is displayed. Type in the value 20 in the field EZ, then click OK to submit. Then, activate Load Combinations by clicking on its icon. The table browser will appear. Create a new Ultimate Limit State load combination by clicking on the New Row icon. Load factors for each load case must be set. Set load factors as follows in the video. Then, create another ultimate limit state load combination with name C0 number 2 with factors again as follows. Finally, create a third load combination by setting a serviceability limit state, SLS quasi-permanent load combination with the following factors. The following table will show after data input. Click OK to finish. Now, the beam should be divided into parts by line meshing, since the type and number of the longitudinal reinforcements can only be adjusted for each part. If necessary, the meshing of line elements can be deleted or modified later. Removing a mesh does not delete loads and properties assigned to the line element. Click on the Mesh tab and select the Meshing of Line Elements icon, which is currently the only active function. Then, select both beam elements with the asterisk button and set the maximum element size to 1 meter. In the bottom right corner, between speed buttons, find the Mesh Display On or Off icon. With this icon, the visibility of a mesh can be switched on or off. Ask for a spatial view from the Views icon on the left, and the following will be displayed. In order to run an analysis, click on the Static tab. Then, click on the Linear Static Analysis icon to run the analysis. Before calculation, the software may warn to save the model if it was not saved previously. The analysis always starts with this warning message. The nodal degrees of freedom must be set if they have not been set before. In this case, the software examines the model and offers a possible setting based on the model and its geometry. Check Save Model with these settings and then click Yes to accept the suggested settings. The calculation finishes with this window. Click on the Statistics tab to see more information about the analysis before closing the window with OK. Then, the following window shows up after clicking on the Display Parameters icon. In the window, input the following settings. Select the self-weight load case and the result component EZ in millimeters. Change the scale by to 10, and then change the display mode to diagram. If we leave display shape on undeformed, the results are drawn to an undeformed model. Then click OK. Change the view mode to XZ mode. The scale of the diagram can also be given or set in the field next to the display mode. Change the scale to 1. Then select the first load combination, C0 number 1. To find minimum and maximum values, click on the min-max values icon. The following window will show up. Select EZ and click on OK. The results panel shows the highest negative deformation and its position. Clicking on OK again will show the highest positive deformation. Click OK again to close. Click on the second drop-down list next to the load case list, and an appropriate result component can be selected for this list. Select internal forces M sub y, and the following diagrams will appear for CO number 1 and CO number 2. For CO number 1, to design the reinforcement of the beam, open the RC Design tab. Click on the Beam Reinforcement Design icon. Select all of the beam elements with the asterisk button, and finally click on OK. In the Beam Reinforcement Parameters window, set the following. In the Cross-Section tab, the cross-section of the beam can be modified if necessary, but please note that the internal forces will be recalculated only if a new static analysis is done. Therefore, this option should only be used if justified. Set the rest of the parameters as seen in the video. In the Parameters tab, set the following. Click on OK to close the window. The software will display a warning message. After taking note of the warning, the beam reinforcement window becomes active in the background. These diagrams are displayed in the Design tab. On the Calculated Beam Reinforcement tab, additional diagrams are displayed. These ones are envelope of reinforcement, cracking, moment resistance, maximum shear force, relative deflection, and absolute deflection. To display other types of results in diagrams, set the display parameters. When determining the distribution of longitudinal reinforcement, the given parameters of rebars and line meshing are considered. By clicking on the Result Display Parameters button, the following panel shows up, where you can optionally choose the diagrams that you want to see. By closing the Display Parameters window, on the Actual Beam Reinforcement tab, the calculated reinforcement can be applied as actual reinforcement. Now, click on that tab to apply the actual reinforcement. Here, the number of longitudinal reinforcements can be modified. Edit boxes allow changing the number of top and bottom rebars in the selected elements. The minus and plus buttons decrease or increase the number of rebars. Select the envelope min-max for ULS combination in the drop-down list next to the Apply Calculated Reinforcement icon. The following diagrams will show up. The software generates the actual reinforcement following the shape of the internal forces by increasing or decreasing the number of rebars. Select the CO number 3 SLS quasi-permanent load combination in the drop-down list, and the deflection and crack width can be queried. Click on the Display Parameters icon and select only the required diagrams. The others should be switched off. Switch on only the display of the model, cracking, and absolute deflection diagrams. By clicking on OK, the following results are displayed considering actual reinforcement. The results for deflection are an approximation, since creep is calculated without considering the effect of shrinkage. A more accurate calculation can be made by nonlinear static analysis, which won't be covered in this video. A detailed description of how to compute a nonlinear static analysis can be found on the PDF Beam Model Tutorial Guide on the AxisVM website.